Okay. Bismillahirrahmanirrahim. So we are going to look at question 13b particularly because the earlier part of the question is pretty standard, the format. Okay. It doesn't mean that it's out of your syllabus. I just thought that I'd skip that part because I want to focus on this part D question as it is something that you have not done before, but you will come across this kind of question. Nitrogen dioxide reacts with ozone in the given balance equation, where you have 2 moles of nitrogen dioxide reacting with 1 mole of ozone, O3, to form N2O5 and oxygen. The rate equation is given. Rate is equals to K times the concentration of NO2 times by the concentration of O3. From the rate equation, you can tell that NO2 is first order and O3 is also first order. Now, because they are first order, it means that they appear in the slow rate determining step, and first order means 1 mole or 1 molecule. Okay, 1 molecule in the slow step. Okay, however, you see that nitrogen dioxide has got 2 moles, right? And that's for later. Okay, I will tell you about it. Okay, so let me just go through this question 13. Okay, because and the question also said that suggests a possible 2-step mechanism. So this is now the reverse. Usually the question asks you to determine the slow step, but this time they give you the rate equation, and the rate equation implies that NO2, 1 molecule of NO2 and 1 molecule of O3 will appear in the slow step. Okay, and the question also said that there are 2 steps in the mechanism. Okay, so it doesn't matter if you put, I think it's easiest to put the first step as the slow step. Okay, and we know that in the slow step, we have 1 molecule of NO2 plus 1 molecule of O3. Okay, so that's what we got so far. It's actually like playing jigsaw puzzle where you have to sort of guess, but you don't just make a blind guess. You have to think about putting the 2 steps, adding them up to give you the overall equation as given in the question. Okay, now since you only have 1 mole of nitrogen, okay, you cannot, that means your product would be N something. Okay, this is the species that we are not sure of, but in this species we know that it contains 1 nitrogen because of this 1 mole of nitrogen. Okay, now if you look at the products, you have N2O5 and O2. Okay, remembering that when you add the steps of your mechanism, step 1 plus step 2, it should be equal to this equation. Okay, so since your N2O5 cannot be your product here because this N2O5 contains 2 nitrogen, whereas here you can only have 1 nitrogen. Okay, so that means your other product would have to be O2. Okay, so this O2 comes from your product, because later on, if I add step 1 plus step 2 overall must give me 2 NO2, must give me 1 O3, must give me 1 N2O5 and 1 O2. Okay, so this O2 is already here, 1 mole of O2. Okay, so I will just highlight that, O2 and O2. Now, this other product would have to be my intermediate. Okay, my intermediate. So if you look at the reactant and each step of the mechanism has to be balanced. So you see here this O2, it may have come from the O3. Okay, to make my equation balance, that means my intermediate would be N O NO3. Do you agree? And you may ask me, what is NO3? Actually, I don't know what NO3 is, but because I know that I need to have 1 nitrogen, okay, to balance on both sides, and my oxygen needs to be 5, 3 plus 2. Okay. Okay, so it looks like this is my intermediate because it's a species that doesn't appear on the chemical equation. Okay, this O2 is one of my products, which is that. Okay, that's step 1. Step 2, if you remember, intermediate produce would have to be later on consumed. Okay, not later on, like immediately consumed. So that means my NO3 will have to react intermediate consumed. Okay, now you remember this nitrogen, there are 2 molecules, and so far I've only got 1 molecule in the slow step. That means I need to add on another molecule of NO2. Okay, to make it, sorry, I will not do that. Add another NO2 to make, to total up. Two mole. Okay. I can hear my echo. I don't know where that's coming from. Okay. And you may ask, why do we add the NO2 on the second step? Well, it's my last step. I need to make sure that all my reactants are in the mechanism and all my products are also in the mechanism. Okay, so I've got my 1 molecule of NO2, second molecule of NO2, done. 1 molecule of O3, done. 1 molecule of O2, done. So that means I'm missing the N2O5. Okay, I need to add N2O5 in my product. However, I also need to make sure that it's balanced. Okay, so you see here, I've got 2 nitrogen, 1, 2, and then my oxygen, I've got 5 on both sides. That means it's balanced. Okay, so if I add these up, if I add the 2 equations up, okay, so overall, step 1 plus step 2 should give me overall NO2 plus O3 plus NO3 plus another NO2 to give me NO3 plus O2 plus N2O5. So you can see that the NO3 cancel out because they appear on both sides of the equation. I get 2 molecules of NO2 plus 1 molecule of O3 to get N2O5 plus O2. So you compare this to your original given equation, which is consistent, which is the same. Okay, so that means your mechanism is correct, right? So it's not as straightforward, but with a lot of practice on writing down the mechanisms, it should be, I think you should be able to do it as long as you uh, tackle the question like you're doing puzzle. Okay, so you have to think about, what do I need to add on the left side, what needs to go in the product side, what could be my intermediate, and etc. Okay, so to answer that question, part D, you don't need any explanation. You just have to write down these two equations. The first step, the slow step, is 1 mole of NO2 plus 1 mole of O3 to form NO3 plus O2. The second step, NO3 will be consumed, your intermediate, that's to cancel out your intermediate, plus another molecule of NO2. If you're wondering, why don't I just add 2 NO2 in the first step? Yeah, because that makes it easy, right? I get it done. Now, if I put 2 molecules of NO2, this means that the NO2 is second order, but my NO2 is first order. The order depends on the number of molecules that appears in the slow step. If I have 1 mole or 1 molecule of NO2, that means it's first order. If I have 2 molecules of NO2 in the slow step, that means it is second order. Okay. The total is 2 moles of NO2, but the second NO2 is not in the slow step, so it's not considered as second order. It's considered as first order still. Okay, so I will just zoom that out a little bit. And for those of you who just joined us, you can copy this down. And later on, we'll have one more question, I believe, that we can practice on working out the mechanism. Okay. So I'll just take the updated attendance. Ayman is here. Fab is here. Ria is here. Najiba. Mailing. Okay. So usually when the question asks us to write down the mechanism, it requires a little bit of thinking, okay, rather than if we were asked to do the reverse, okay. Usually most questions, they give us the mechanisms and then we have to write our rate equation given the slow rate determining step, okay. The opposite is slightly a little bit complicated, but again, it's not impossible for you to do. You can do it. Over time, it will get easier, I feel. Okay. Okay, please let me know when you're done copying that part. After that question, we will be looking at question 14. Okay. Question 14, no graph to plot. Okay, that's fine. Are you done? Can we move on? Okay, thank you. Right. So this is the reaction with hydrogen with iodine to form 2 hydrogen iodide. A small amount of hydrogen is mixed with a large excess of iodine. So then you plot the concentration of hydrogen over time, and you get a concentration time graph, okay? And if you see a concentration time graph that is a curve, it is not zero order, okay? That's one thing for sure we can say, it's not zero order. Okay, suggest why a large excess of iodine is used in the experiment. Okay, so usually when you use a reagent that is in a large amount or in excess, the reason for this is because you want the concentration to stay constant, okay? So that because it contains in a large amount, only a small proportion of it will react so that we keep the concentration of the iodine constant. Okay, so the reason for that. So concentration of iodine stays constant. Okay, the next part, the reaction is first order with respect to hydrogen. Use data from the graph to confirm this statement. Okay, so now they're telling us that hydrogen is first order. The only way we can confirm that it's first order from a concentration time graph is by looking at the half-life. Okay, so we're going to look at the half-life. You are starting at concentration 8. You want to go down to 4 and then go down to 2. Okay, it's the time taken for your concentration to go down by half. So at 8, the time is 0. At concentration 4, the time is somewhere there. Okay, and then at the concentration 2, the time is somewhere there. I need my calculator. So that looks like around 40, 47, 49, 48. And then the second half-life looks like it's at 90, no, actually. I will redraw my graph because I think it's there. Module. What sort of number are you getting? That looks like, I don't know, 95. You can do another one if you're not convinced at concentration 1. I feel like the graph is not great. So 1, and then maybe here. That looks like just below 150, 149. 90. This is 90, so that looks like 93, and then 149. So let's see. Oh, that's a bit off. What numbers are you getting? The range in the mark scheme should be between 45 and 55. Did you get those numbers? 45 to 55. Again, it's not that constant, okay? But the question already tells us that it's first order, so we just have to sort of lie and say, well, look, the number is constant, okay? Let's see, 93. Well, I'm just gonna say 141. Okay, so actually you don't need three half-lives. You only need 2 half-lives. Okay, use the data from the graph to confirm this statement. So we will say that the half-life is constant at whatever value you got, 45, between 45 to 55 seconds. Okay, so the axis is in second. I know the numbers are actually not that constant, okay, but the question is already telling us that hydrogen is first order. So do not change the question and say my half-life is increasing. Okay, so you must say that the half-life is constant because that is the criteria for first order. And the most important thing is your working construction lines must be shown. Must be shown. Okay, so you can label this T half 1 and T half 2, and that's enough. Okay, just 2 half-lives should be enough. And for 2 marks, 1 mark is for showing your working in the graph, okay, showing the construction lines, and the second mark is for saying, well, the half-life is constant, even though it's not, but we're just going to say it's constant. Okay, as long as you stay within the range of 45 to 55 seconds. Okay. Next, we are going to look at the next page, where we are given 3 experiments, and then we're given the concentration of hydrogen and iodine. So we already know that hydrogen is first order. Okay, so we need to, okay, forgot to erase that. I was doing it last night. So we know that hydrogen is first order. We want to find the order of iodine. But if you look at experiment 1, 2, and 3, there is no 2 experiments that only changes the iodine. Okay, if you take 1 and 2, the hydrogen and the iodine changes. Okay, if you take 1 and 3, same thing, hydrogen and iodine changes. If you take 2 and 3, also both hydrogen and iodine changes. Okay, so there is, so this is where we where the combined effect comes in. Okay, so the easiest, I will take 2 and 3. Okay, you can always take 1, 2, 1, 3, whichever, but I'm going to take 2 and 3. Okay, to do this, in a quick way where you, if you're already confident, okay, you will take the increase in the concentration of your hydrogen from 5 times 10 to the power of minus 1, okay, divided by 1 times 10 to the power of minus 1. That is an increase in 5. Okay, same thing, my iodine increase in a factor of 5, or times 5. But I know already, remember that my hydrogen is first order. And then I want to find how much my rate has increased. So again, take the bigger number, which is the bottom number, minus 14 divided by 2 times 10 to the power of minus 15. So that is an increase in 25. Okay, so this increase in 25 is actually a combined factor of an increase in hydrogen and an increase in iodine. Okay, so since we increase hydrogen by 5, okay, so our rate should also be affected by increase in a factor of 5, since it is second order. The next effect, okay, the remaining effect would have to belong to iodine. Okay, so that means 5 times 5 to give us an increase in 25. Okay, so that means the effect of increasing concentration of iodine is also times 5. And you can see that increase in concentration and increase in rate is directly proportional. It's the same. However much you increase your concentration, the same increase will have an effect on your rate. So that means, so this is an example of combined effect. You must not ignore the change of hydrogen. Just because you already know hydrogen is first order, you cannot say, oh, okay, I'm going to ignore hydrogen now because I already know what it is, right? But don't forget, this change in rate is affected by the change in hydrogen and the change in iodine, okay? I hope by now you are already okay with the combined effect. Use the data, okay, to deduce the order of reaction. Explain your answer. Okay, so we will say that the reaction is first order with, okay, I will just say experiment 2 and 3. Okay, concentration of hydrogen increases by a factor of 5, or increases by 5. Iodine increases by a factor of 5 as well, or you can say by 5 times. It means the same thing. The rate increases by a factor of 25. Since H2 is first order, iodine increases the rate by a factor of 5 as well. So the order with respect to iodine is first order. Okay. So you must mention, so in the marking scheme, it says any two rows of the data quoted. So we have chosen experiment 2 and 3. We also must mention the effect of hydrogen. So we also mention that hydrogen increases by a factor of 5 and hydrogen is first order. So that means if it increases by a factor of 5, the rate also must increase by a factor of 5. Okay, so that's your second mark. Your third mark, the effect of iodine specified and linked to first order. So we say that iodine increased the rate by a factor of 5. So that's our third mark. Okay, so please make sure you don't just skip. Okay, even though your answer is already correct, you say first order, but because your explanation is not enough, your points are not enough, that cause you to lose marks. Okay, so this is common for students. They got the order right, but they don't know how to express their answer in the explanation box, okay, in the answer box. But I can see they're working, and their working is actually correct. Okay, use the information, write the rate equation, use your rate equation to calculate the value of the rate constant. I think that one we are okay. Let's just do that quickly. Rate is equals to K times the concentration of hydrogen, first order, that means power 1. Iodine, first order, that means power is also 1. Use your rate equation and data from experiment 1 to calculate the value of the rate constant. Okay, so this is also something that you should already be comfortable doing. So they want you to use experiment 1. Actually, if you use experiment 1, experiment 2, or experiment 3, you will still get the same K because K is rate constant, but you must follow the instruction. If they want you to use experiment 1, then you use experiment 1. So experiment 1, the rate is 2 times 10 to the power of minus 17, K times by the concentration of the hydrogen, 1 times 10 to the power of minus 2, and iodine is also 1 times 10 to the power of minus 2. Okay, and then you just rearrange K and work out its units later on. Okay, I want to move on to part C. Okay, so I will just write down rate is equals to K times H2 times by iodine. Okay, I'm moving on to part C now. Still on the same question, question 14. You can imagine that this question is a long question. Okay, at 400 Kelvin, the rate constant for the forward reaction is approximately 1000 times greater than the rate constant for the backward reaction. So if I were to write this down in an equilibrium, it would look like this. Okay, so forward, the rate constant is bigger than the backward rate constant. Now, if you remember, if the rate constant increases or big, that means your rate is also faster. Okay, your rate is also bigger. So rate and rate constant, they are proportional. Use this information to explain what will happen if equal concentrations of HI, H2, and iodine are mixed at 400 K. So initially, you have the same amount of initial concentration. You should comment on the relative initial rates. So we already know the relationship between rate and rate constant. The position of the equilibrium reach. So that means we know that the forward reaction is faster. Okay, and the reverse reaction is slower based on the value of rate constant, right? So first we want to comment on the initial rate. We will say that the forward reaction is faster than the backward reaction. We also need to comment on the position of the equilibrium. Since the forward reaction is fast, that means more products will be formed. Okay, so the equilibrium the position, equilibrium position reached will be on the right side or the product side. Okay. Okay. Next, at 700 Kelvin, so this time we're going at a higher, it's still the same system, but we're increasing the temperature. The rate constant for the forward reaction is approximately 50 times greater than the rate constant for the backward reaction. Okay, so we need to compare because we want to know, deduce the signs of the delta H values of the forward and backwards reaction. Okay. So at 400K, H2 plus I2 to HI. Okay. Now I know they are just relative size. Okay. So I will say that the forward reaction is times 1000. Okay. And then at 700K, the forward reaction is now 50 times greater. I know I am comparing it with the backward reaction, but the number decreasing is also saying something. Okay, the rate constant is decreasing. And remember, rate is proportional to K, rate constant. So if you notice that as temperature increases, rate decreases. Do you agree? At 400 Kelvin, the rate constant, I know it's rate constant, but I can also talk about the rate. The rate constant is 1000 times faster than the backward reaction. At 700 Kelvin, the rate constant forward is only 50 times greater than the reverse reaction. So as temperature increase, the rate decreases. Okay, that means what happens? It is now starting to favor the backwards reaction. Okay, so temperature increasing, the forward reaction is less favored. Okay, forward reaction is less favored. If we remember from our Le Chatelier's principle, an increase in temperature will favor the endothermic reaction. Remember? Okay, so that means if the forward reaction is less favored, the forward reaction would be exothermic, which is negative. Do you agree? Yeah?
Yes.
Okay, good. So that means the sign, the delta H, usually the delta H is for the forward reaction, would be negative. Okay, and explaining our answer, we will say the forward reaction, wait, what does it want? This deduce the signs of the delta H values of the forward and backward reactions. Okay, the forward reaction is negative and the backward reaction is positive. Okay, the reason for this is as temperature increases, the forward reaction is what do I say? The forward reaction is less less favored, but it's talking about the speed actually. The forward reaction has smaller the forward reaction is actually they just want us to talk about the equilibrium position. So less favored lah, because we're talking about the position. The forward reaction is less favored. Position of the equilibrium shifting to the left or the reaction side. Okay, and this implies that the backward reaction is endothermic. Okay, so let me repeat that. Okay, so if you look at 700 Kelvin, your rate constant of the forward reaction is now 50, whereas in 400K, your rate constant was around 1000. Okay, the reason why this number is decreasing is because the backward reaction is increasing. Okay, but it's still bigger. The smaller the forward reaction is bigger than the reverse reaction, but the fact that the reverse reaction is increasing indicates that it is being favored at high temperature, and high temperature usually favors endothermic reaction. So that's why we have implied that the reverse reaction is a positive delta H and the forward is negative delta H. In a way, you can see it as like the reaction is more favored and less favored. Okay, but I try to talk about the rate more importantly. Okay. Right, let's see what is on question 15. Is that a long question? I feel like, oh, that's a long question. Yeah, okay, so I will not touch question 15 today. So I will continue with question 15 tomorrow.